let us start the mesh current analysis method. A mesh current analysis method is just like the node voltage method. However, here we actually use the current which flows on the periphery of each individual mesh. So instead of a node, we shall apply hypothetical currents which are known as the mesh current. A mesh current may or may not be the actual current which is present in a given circuit. Also, rather than applying the Kirchhoff's current law at each node for the application of mesh law or the mesh current analysis method, we shall apply the Kirchhoff's voltage law for each of the mesh. So let us see how we can solve a given circuit. Suppose that we have this particular circuit. So to see what is the total number of required mesh equations for this particular circuit, we first need to calculate what are the total number of nodes and what are the total number of branches in this given circuit. So if you see here, we have this node 1 here, 2, this node 3, this is node number 4, and this is node number 5. So there are total nodes is equal to 5, and there are 7 branches in this given circuit. Remember that the number of branches is equal to the total number of elements in a given circuit. So branches is equal to, we have 7 branches here. So the expression here is that the total number of total mesh equations required is equal to b minus n minus 1. So there are 7 branches here, and then there are 5 nodes here. So we require to have 3 mesh currents in this to solve this given circuit. The next thing is that just like the node voltage method, we have to actually adopt some uniform strategy to apply the conventions on this particular circuit. For example, we shall assume that all the mesh current are actually flowing in a clockwise direction, number 1. Number 2, we shall then apply the same principle that we used for to designate the voltage rise and voltage drop in a given mesh of this circuit. So as a first instance, let us say that we have 3 currents moving here. So this is the first current, this is the second current, and this is the third current. Let us say this is IA, this is IB, and this one is IC. So we have now 3 currents, and if we solve for these 3 currents, we can solve any parameter in this circuit. Moving on with this particular thing, let us write the equation for mesh A and mesh B and then for mesh C. Equation for mesh A gives us, if you see that this current IA is entering the negative terminal of this 40 volt source, and hence using the passive sign convention we shall consider it a voltage rise. So we have minus 40 plus the drop across this 2 ohm resistance, so 2 times IA, and then we have a drop across this 8 ohm resistance. Now if you carefully look at this particular circuit, there are 2 mesh currents which are associated with this particular resistance. One is this IA and the second one is this IB. If you further notice that this IB is entering this 8 ohm resistance in the direction opposite to that of this current IA, and while we are writing the equation for the mesh A, the voltage drop across this 8 ohm resistance shall be designated as plus 8 times IA minus IB, and thereafter the loop is closed and the application of Kirchhoff's voltage law is finished. So that becomes equal to 0. If we actually rearrange this particular equation for the variables that we are using here, we can notice here that we have 10 times IA minus 8 IB plus 0 IC, and that is equal to 40. So let me call this one equation number 1. Mesh A is not sharing any element with that of the mesh C, and therefore there is no component of mesh C involved with the first equation. Now let us write the equation for mesh number B. For this mesh number B, we have 8 times IB minus IA. While we are writing it for IB now, so we have to give preference to this IB, so that's why we have taken it IB minus I of IA. And also because this 8 ampere, this 8 ohm source has currents in opposite direction, then we have a drop across this particular resistance plus 6 IB plus 6. Again, applying the same particular convention that we have IB entering this 6 ohm resistance from the top side and IC flowing into this resistance 6 ohm from the bottom side, and therefore we have plus 6 into IB minus IC, and that is equal to 0. Now if I further rearrange this particular thing, we have 20 times IB minus 6 times IC minus 8 IA, that is equal to 0, and this is my equation number 2. Similarly, we can write the equation for mesh number C. So equation for mesh C, that is equal to 6 times IC minus IB plus 4 times IC, and because this mesh current is assumed in a clockwise direction, so it is entering the positive side of this 20 volt source, so therefore it is plus 20, and that is equal to 0. So if I rearrange this equation as well with respect to the mesh current variables, then we have 0 IA minus 6 IB plus 10 IC, that is equal to minus 20. Now that we have three equations and there are three unknowns, we can adopt the Cramer's rules using the matrix. So we first need to rearrange these 1, 2, 3 equations in terms of a matrix, and thereafter we can solve that particular equation. So in terms of the matrix we have, we can say we have 10 minus 8 0, then we have minus 8 20 minus 6, and we have 0 minus 6, and this last one is this 10, and here we have IA IB IC, and that is equal to 40 0 and minus 20. So now we have this particular equation, which is quite a normal equation for engineering students, so we can solve it. Now solving this particular equation, we IA equals to 5.6 ampere, we have IB that is equal to 2 ampere, and then we have IC that is equal to minus 0.8 ampere. Now if we see here, earlier we have said that a mesh current may or may not be the actual current that is flowing through those elements. So if you see here, IA, the value of IA is same for this 40 volt source as well as for this 2 ohm resistance. However, the current flowing through this 8 ampere, the actual current which is flowing through this 8 ampere, or if I say that I want to compute what is this I phi, let us say, so this I phi is equal to, because this is in this direction, it is required to find out in this direction, so it is in harmony with this IA, so that is equal to IA minus IB. So that will be the actual element current flowing through this 8 ohm resistance, right? Rest are two are actually the mesh current, and we have earlier claimed that the mesh current may or may not be the actual current flowing in the circuit. So for the condition where it is actually the actual element current, it is only for that where there is no shared current with it. However, with this 8 ohm resistance, we have this IB sharing the 8 ohm resistance, so therefore their difference will actually constitute the actual current flowing through this particular resistance of 8 ohm. So now we have I phi is equal to IA minus IB, and that is equal to 3.6 ampere, right? So for instance, if we are asked to find out what is the power which is delivered by each of the sources, then we can actually find this by applying this simple expressions of P is equal to VI. So for a 40-volt source, the current is leaving the positive terminal, as you can see here. The current is leaving this positive terminal of this 40-volt source. So we have the power associated with this 40-volt source is equal to 40 times 5.6, and that is equal to 224 watt. 224 watt, and it is actually delivering the power because the current is leaving the positive terminal. So the power will be in terms of this negative sign. So this is first thing that we have actually seen for the mesh current analysis method. Let us apply and let us see how we can solve further circuits using the mesh current analysis method. So let me draw another circuit here. This time we assume that we have a dependent source connected in our circuit. So with this dependent source connected in our circuit, let us say we have, this is 50 volt, this is 5, this is 20, and we say this is I5, right? Let us say this is I5. So as a first step, we shall assign the mesh currents here. Again, if you count the total number of branches in this circuit, we have this is branch 1, 2, 3, 4, 5. So the total number of branches are equal to 5, and there are 1, 2, 3, and there are 4 nodes available here. So nodes is equal to 4. So going with that particular expression, we have B minus n minus 1 equations are required. So that is equal to 5 minus 4 minus 1. So that is equal to 2. So there are two mesh equations that are required to solve this given circuit. So now these two equations are obvious. So we have this as IA, we have this, let us say this is IB, and we shall write the equation for this circuit. I will leave the exact solution to you to solve it using your own mathematical skills. However, I would like to emphasize what is the procedure if there is a dependent source which is involved in solving a circuit using the mesh current analysis method. So right now let me write the equations for this mesh A. For this mesh A, we have minus 50 volt because the current is entering the negative terminal here. It is entering from this side. Then we have plus 5 IA plus 20 times IA minus IB, that is equal to 0, because the current is actually entering the 20 ohm resistance from the top side, and from the bottom side we are having this IB. Suppose that if you assume that IB is actually a clockwise, it is not a clockwise current, rather it's an anti-clockwise current or counterclockwise current, then we will just make this negative sign, we will replace it with the positive sign, because now both the current is entering this 20 ohm resistance from the same terminal. So that will not make any difference in the end result, because the numbers not lie, and these methods are quite robust in giving you the exact particular solution. So if I now expand this particular thing, then we have 25 IA minus 20 IB, and that is equal to 50. So this is my equation number 1. Regarding the mesh for the second equation, let me write it for mesh B as well. Writing it for mesh B, we have let us say this is 20, sorry, for this mesh B we have 20 times IB minus IA plus 4 times IB. Now because it is entering this positive terminal of this voltage current control voltage source, we have this plus 15 times I5, and that is equal to 0. In here we need to actually replace this I5 in terms of the mesh current I and IB. And remember that this I5 must be some current flowing in some element in the same circuit. So if we carefully examine this particular equation, we come to know that this is the I5, and it is actually the current flowing through this 20 ohm resistance. So with our instinct, we should notice one thing instantaneously, that this I phi is equal to IA minus IB, because this IA is in the same direction as that of the of this I phi. So I phi is equal to IA minus IB. So so let us substitute it in here. So we have this 20 times IB minus 20 times IA plus 4 times IB plus 15 times IA minus 15 times IB, and that is equal to 0, right? I have just simply I have substituted this equation in here in place of this I phi. So I will get what I will get is let me add the IA first. So that is plus 15, this is minus 20. So we have minus 5 IA, and then we have 24 minus 15 is equal to plus 9 times IB, and that is equal to 0, and this is my equation number 2. So now we have two equations, we have two unknowns, so it is quite easy for you to solve this equation. You can, once you have solved for this IB, you can thereafter calculate each and every aspect of every element, including the power, the voltage, the current. You can then apply the Kirchhoff's current law on this particular node, and thereafter you can also apply the Kirchhoff's voltage law to verify if your answer is correct or not. You can further examine this by applying the by computing the total power which is consumed and delivered by each of these elements, and thereafter you can see if the Taylor's theorem is validated for this particular circuit or not. Let me go ahead with another circuit here. For example, if we have a circuit where a current source is common with a mesh, then it actually simplifies the given solution. So for example, if we for this particular circuit, you see we have to assume two mesh currents available here based on the equation as well as based on your instinct, because there are two mesh, so you need to identify the currents for these two mesh. So let us assume this is IA and this is IB, right? So we have assumed that there are two currents here. The one is IA and the second one is IB. Now, if you carefully looking into this particular circuit, the value of this IA cannot be different than that of this current source IS, right? Because that contradicts the definition of an ideal current source. So a current source actually enforces the same amount of current through itself, and therefore it is not possible that IA has a value different than that of this current source IS, and therefore we are left with only one equation. So if we have for any circuit having a current source only with a single mesh, not sharing between the two mesh, because that is another concept that we shall see after a short while. So for this particular circuit we have IA that is equal to IS, right? So whatever is the value of this source current is the value of this mesh current IA. So what are we left with? We are only left with the solution of this IB, right? So if I write the equation for this IB, let us say this is R1, this is R2, and this is Vs, then the equation for this IB is R1 into IB minus IA plus R2 into IB plus Vs, and that is equal to 0, right? And this is the only equation which is required to solve this given circuit, because the value of this IA is already known, right? So we have only one equation to solve. The other equation is already solved because of the virtue of, because we know what is the value of this IS here. So this is one thing that I want to elaborate. Let us see if we have a current source which is shared between the two adjacent mesh here. So I have a given circuit here. Let me draw a circuit. So let us say we have this. We have this circuit. So let us say this is 3, this is 2, this is 6, this is 4, this is 50, this is 100. Now in this given circuit we have two mesh that we need to solve, but the problem is that we have a current source common between the two adjacent mesh. So first of all, let us assume what is IA and what is IB. Let us say this is IA and this is IB, right? Let us first solve it through the conventional method. That what if we do not go for some other technique? So how can we actually solve this given circuit? Now, similar to that of a node voltage method, where we actually assume some current flowing through that voltage source, which is common between the two nodes. In this particular mesh current analysis method, we shall assume some voltage which is available over the particular current source, right? That is very important. So now let us assume that we have some voltage here, and that voltage here has this polarity. It is written like this one. Now, if I write down the equation, for IA for mesh A, I will write down the equation here, and for mesh B, I shall write down the equation here. So for mesh A, we have minus 100 plus 3 IA, and then this is entering the positive terminal of this voltage source. So this is plus V, then plus 6 times IA, and that is equal to 0. This is my equation for mesh current A, right? For mesh current B, we shall write the equation on the similar grounds. So let me write down the equation. We have minus V plus 2 times IB plus 50 plus 4 times IB, and that is equal to 0. This is my equation number 2, and this is my equation number 1. Now, if I add these two equations, I will simply get rid of this sign V, right? So now, adding the equation number 1 and equation number 2. So if I add the two equations, I have 3IA, rather this is 9 times IA plus V, that is equal to 100. Here we have 6 times IB minus V, and that is equal to minus 50. If I add these two equations together, I will get rid of this V, and the resultant thing here is that it will be equal to 9IA plus 6IB is equal to 50. So this is the equation that I will get. Now, to solve this given circuit, this is one thing that we have reached this particular equation, and let me call this equation number A. We need to have another information also to solve this equation A, and that is by observing this particular circuit, we come to know that the current source which is shared between this mesh A and mesh B is actually the difference between the mesh current A and mesh current B. And because the direction is upwards, so it is having this current IB. IB is actually entering in the same direction as that of the current as that of the source. So this IS, if I say this is IS, let me call this IS, and let us say this is equal to 2 ampere. Let us say this is 2 ampere. Then I shall say that IB minus IA is equal to 2 ampere. This is the another condition which is required to solve this given circuit, right? So we have the first equation, which is 9 times IA plus 6 times IB, that is equal to 50. But this single equation is not capable of giving you a solution. So we need another constraint, right? What is that constraint? That constraint is that the difference between the mesh current A and mesh current B is actually the value of the current source, which is common between the mesh A and mesh B, right? So we have this another equation equation available, that is IB minus IA is equal to 2 ampere, and based on this equation A and equation number B, you can then solve this given circuit. That is by virtue of the conventional method, if there is no if we do not apply with the concept of the super mesh that I'm gonna explain now. So there is a concept which says that if a current source is common between two or more mesh, of course it will be a two or more mesh, then a super mesh can be established. right? And by mean of this current source, this source could be an independent or a dependent source. But it has to be the current source, right? It has to be a current source. So let me redraw the circuit again that we have drawn here, and then we shall apply the equation for the super mesh. So we have a voltage source here. We call this 100. Then we have 3 ohm here. Here we have the current source. The value of that current source is equal to 2 ampere. And then we have a resistance here. This was 6 ohm. Then we have this 2 ohm. This is 50. This is 4, and that's it. So now let us assume we have this is IA, and this is IB, right? So I shall actually create a super mesh by virtue of this particular current source. So first of all, I would in the same fashion that we did earlier, I will first write down the equation for this IA. Starting with this IA, we have minus 100 plus 3IA plus 6IA. Skipping this 2 ampere current source, I will move directly to this IB, right? So if I move directly to the IB, we have plus 2IB plus 50 plus 4IB, and that is equal to 0. If I simplify this particular equation, I will get 9 times IA plus 6 times IB, and that is equal to 50. And this equation is essentially same as that of the equation that we have actually that we have showcased earlier. This is exactly the same as that of this equation number A, right? So the second constraint, which is elaborated in this equation number B, shall remain the same. So that is how we can actually simplify a given circuit by applying the concept of a super mesh. Remember that this concept of super mesh can only be applied if there is a current source common between the two adjacent mesh. If there is a current source independent or dependent, it does not matter, but we cannot do it if we have a voltage source common between the 2 points, right? So that's all for this mesh current analysis method.